This is a topic on functions. In a prior unit, quantitative reasoning, we used three ways of describing data: a table, a graph, and a formula. Each description has advantages and disadvantages, but all are valid. So here you see a picture of data displayed on a table. Here's data displayed on a graph, and here's data displayed in a formula. These are also the three primary ways used to describe a function: a table of data, a graph of those data, and a formula. Additional ways will be discussed later. Now in this graph, graphs can be curves. You're seeing a picture of a straight line, but also graphs can be individual points, sometimes known as a scatter plot. All of those are graphs that represent functions. These all meet the first requirement of a function. Given the value of an independent variable, in this case t, the value of the dependent variable, in this case s, is determined. Here's the key point. There is only one value of s for each t. For a relation to be a function, the independent variable, often denoted as x, can only result in a single value for each dependent variable, often denoted as y. For instance, if s is a function of t, then the value of s, the dependent variable, is uniquely determined by the value of t, the independent variable. This is a key point right here. There is only one possible value for s for each given value of t. If there were two possible values of s for a given value of t, then this would not be a function. It would just be a relation. A function is a special case of a relation. The critical test as to whether a relation is a function is whether each x value has only one corresponding y value. Here's an example which might help illustrate the point about what is a function and what isn't a function. Imagine a soda machine. For every button you push, and in math world we refer to it as an input, there's one type of soda. Again, in math world, we refer to it as an output. There can be more than one button for the same type of soda, but there cannot be more than one soda for each button. As you see in the picture, we have two cola buttons and we have two diet buttons. Generally speaking, the soda's machine input-output device is a function. For each input, there is one and only one output. Now, upon occasion, we've all experienced where we pressed a button and two different sodas have come out. That would not be a function. We would just refer to that as a relation. A function occurs when you press a button and one soda comes out. Example number 1. Two of these tables represent a function and one is not a function. The explanations are shown below each table. So in our first table here, we do have a function, because each x value produces a unique y value. So when you look here, you'll notice that we have negative 11 has one answer, 3. Negative 5 has one answer, 4. 3 has one answer, negative 5. 4 has one answer, 9. 5 has one answer, 7. So all of these inputs have one unique output. The second table also represents a function. Each x value produces a unique y value. Now notice that the same y value result from different x values doesn't matter. So here we see the 2 is represented 3 times, but the input 1 only has one answer. The input 6 only has one answer. The input 12 only has one answer. So if you think of it this way, if this is a person and these are birthdays, each person has one birthday. That's fine. It's possible for people to share birthdays. It's possible for more than one person to share birthdays. That's okay. But it would be odd if one person had two different birthdays. The fact that one person each has one birthday, one input has one output, makes that a function. Now in this table, we don't have a function. The x value of negative 1 produces two different y values, 5 and 9. So this is not a function, this is a relation. I'll highlight that right here. See, negative 1 has an output of 5, and -1 also has an output of +9. Because -1 has two different outputs, this is not a function. This would be like saying one person has two different birthdays. Graphs can also be used to determine whether or not a function is represented. To do that, we use something called the vertical line test. To determine if a graph describes a function, see if any given x value provides more than one y value. Graphically, that test is done by seeing if a vertical line placed anywhere on the graph touches it in more than one place. If it does, that means there is more than one y value for a given x value, and it is not a function. Which of these is a function? The first graph describes a function since the purple vertical line cannot be placed so as to touch the graph in two places. If we look at this graph on the left, this describes a function. The purple line, no matter how it slides from left to right, only intersects the graph at one point, right here. So this describes a function. The second graph does not describe a function, since the purple vertical line has been placed so as to touch the graph in two places, so that the value of x yields two y values. So if we look at this vertical line, we notice it touches the graph in two spots, here and here. So this x value has two y values, one above it and one below it. That's why this is not a function. The vertical line test. Example number 1. The vertical line test is used to determine if a graph represents a function. The graph of a function can only touch the graph in one place. If it touches the graph in more than one place, it is not a function. Just for clarity, for both of these graphs, this red line is the graph of the function, and this blue line is the graph of the relation. The purple line represents the line we're using for the vertical line test. So on the left, this is a function. The vertical line cannot be placed anywhere on the graph such that it touches in two places. So if I take this purple vertical line and move it from left to right, there's nowhere on this graph where it's going to touch more than once. It only touches the graph one time. However, over here on the right, this is not a function. A vertical line can be placed in at least one location such that it touches the graph in more than one spot. So again, this blue line represents the graph of the relation. This is the purple vertical line we're using for our test. And since it touches here and here for this given x value, we rule out a function. This relation is not a function because it fails the vertical line test. Graphs, practice number 1. Do either of these graphs describe a function? Here's a chance for you to pause the video and make that determination. Use the vertical line test to decide if either of these relations represent a function. Pause the video. When you've decided, resume watching the video to compare your answers with what you see on the screen. And welcome back. So on the left side over here, this does describe a function. A vertical line cannot be placed anywhere on the graph such that it touches in two places. So we introduced this purple vertical line to determine whether or not this is a function. And as I move this vertical line from left to right or from right back to left, nowhere will this purple line intersect the graph in more than one spot. So therefore, this is a function. However, over here on the right side, this is not a function. A vertical line can be placed in at least one location such that it touches the graph in more than one place. So if we take a look at our test line, that's this purple line is a test line, we notice that it touches the graph in two spots, here and here, for this given x value. Since it touches in more than one place, the vertical line test rules out the possibility of this being a function. Practice number 2. Are either of the graphs of these relations the graph of functions? Pause the video. Use the vertical line test to make your determination, and then once you've decided whether or not these are functions, or any combination of these are functions, Resume watching the video to compare your answer with what you see on the screen. And welcome back. Because both fail the vertical line test, neither of the graphs represent a function. So we've introduced this purple line right here to use the vertical line test, and I specifically went for this specific x value right here because this x value has two y values, one above it and one below it. It fails the vertical line test, so the graph of this relation is not a function. By the way, when we talk about graphs, we are referring to all types of graphs. It could be scatter plots where they're discontinuous like this, or continuous where you have a line going from one end of the graph to the other. Speaking of this second graph, this is also not a function because when I introduce the vertical line for this particular x value right here, we see there's actually several y values above it and below it. The vertical line intersects the graph at many points. And if you can picture in your mind sliding this vertical line over to here to this x value, again, there's several y values up along this line here associated with this one x value. The vertical line would intersect all the way from here to here, giving it many places of intersections. Therefore, this also fails the vertical line test. So this is also not a function. Formulas. Example number 1. For a relation to be a function, the independent variable, often denoted as x, can only result in a single value for the dependent variable, often denoted as y. Let's take a look at a few examples here. In example A, we have x equals 19. Now this is not a function. When x equals 19, there are infinitely many values of y, not just one. Graphically speaking, if we were to graph x equals 19, this would be a vertical line at x equals 19. Since it's a vertical line, it would not pass the vertical line test, so on a graph we could see it's not a function. Taking a look at example B, y equals x cubed, this is a function. For any value of x, there is only one value of y, and that would be whatever x cubed is. So for whatever number you replace x, you're only going to get one y. For every input, there's one unique output. The same thing can be said for example C, y equals 4. For every value of x, there's going to be one unique output, 4. And remember, we said outputs can be shared. So even though all the x values will be 4, there's only one unique output for each x value. So this is a function. There are infinite value of x's, but there's only one value of y equals 4. So this does count as a function. D, however, is not a function. When x is equal to 9, there are two values of y, 3 and negative 3. So the input has two different outputs. Therefore, that violates the definition of a function. Now, what I'm about to say is good for beginners who are trying to identify functions. This will be modified as you get in higher level math classes, but for starters, this is a good rule of thumb to follow. You'll notice I highlighted both example B and C. Rule number 1, just for starters, you want y to have an exponent of 1. You want y to the first power. If y has any other exponent other than 1, it is not going to be a function. The other thing we want to keep in mind is that y cannot have a coefficient of 0 as we have here. Okay, so if I write this as 19 plus 0 times y, this also would not be a function because you would have a vertical line and you would also have an infinite many values of y, not just one. So there's two ideas to keep in mind for these beginning stages. This is not a hard, fast rule, and like I said, as you learn higher level math, this is going to be changed somewhat. But in the beginning stages for Algebra 1, it's a good idea to keep in mind you want to look for y values that have an exponent of 1 and not a coefficient of 0. Formulas practice. Determine if each of these formulas represent a function and provide an explanation to support your answer. So here's an opportunity for you to practice by pausing the video, go through examples A through D, and determine whether each one is a function, and if it is or isn't, explain why. When you have your answers, resume watching the video to compare your answers with what you see on the screen. And welcome back. Now the first one is a function. For any value of x, there is only one value of y, and it's whatever answer you get when you replace x into 3x minus 2. So for every input, there's one unique output. Letter B is also a function. For any value of x, there's only one value of y, 2. Each input has its own unique output, 2. Now, even though those outputs are shared and common all the way through, that's fine. You're not having two different answers for an x value. Now, when we get to choice C, we find out that that is not a function. When x equals 4, there are infinitely many values of x, or of y, not just one. And also remember that this is a vertical line at x equals 4, and a vertical line would not pass the vertical line test. Speaking of graphs, y equals 2 would be a horizontal line at y equals 2, and that would pass the vertical line test if we're talking about graphs. Finally, let's go to y equals x squared. That is a function. For any value of x, there's only one value of y, and that would be x squared. You put a number in for x squared, you're only going to get one answer. Now remember, when we talked about the an idea for beginners, these all have exponents of 1. And when you're in the beginning stages of identifying functions, you notice that you want y to have an exponent of 1. In example C, the second rule is that you don't want to have a coefficient of 0. And that's what's happening here. We have a coefficient of 0. So that's why C is not a function. So keep in mind you want to have y to have an exponent of 1, but not a coefficient of 0. Graph of points practice. A function is shown in the coordinate plane. Which additional point or points can also be added to the graph so that the graph continues to satisfy the definition of a function? Select all that apply. So here is an opportunity for your practice. Pause the video. Make your selections of point or points that would be added to the graph, yet still allow this to satisfy the definition of a function. When you have your answer, resume watching the video to compare your answers with what you see on the screen. And welcome back. Let's advance the slide and see what the answers are. The circled points are shown on the graph along with purple vertical lines, showing that the new points leave this as a function. No x value has two y values. So just take a moment and look at the graph. Notice that the points that are added, for example, here we have -1, 3, and it passes the vertical line test. Up and down, there's no other y values for this x value, x equals -1. When we add 1, 1, again, this also passes the vertical line test. Moving up and down the line, there are no other y values where x equals 1. And finally, for 4, -2, it also passes the vertical line test. There are no other y values when x is equal to 4. Now let's see about the other functions, or should I say other points. The uncircled points are shown on the graph along with purple vertical lines showing that those points would not leave this as a function. Each x value would have two y values. So when I add -3, 4, there's -3, 4 up here, notice there's another y value at x equals -3. That violates the definition of a function. The same can be said for 0, 1. When I put 0, 1 onto the graph, you'll see that this is not a function because it doesn't pass the vertical line test. When x equals 0, we have two outputs, 1, -1. That violates the definition of a function. And finally, for 2, -1, sorry, I looked at the wrong one. For 2, -1, this also violates the vertical line test because when x equals 2, we have two different outputs, 3 and -1. So therefore, that also doesn't allow this to be a function. Tables of points practice. A function is shown in the table below. Which additional point or points can also be added to the table so that the table of values satisfy the definition of a function? Select all that apply. So you'll notice there are empty spots here at this table. You're going to go through this list of options from A to F and decide which point or points can be added into these blank spots while still maintaining that this table remains a function. Pause the video, make your selections, and when you have, resume watching the video to compare your answers with what you see on the screen. And welcome back. Let's take a look at the answers. The green circled points have different x values than the previous points in the table, so would not lead to one x value having two different y values. Let's pause here and try this. If I select option C and put 0 in for x and its corresponding y value of -4, I notice that there are no other x values of 0 in here. So 0 only has one unique output, one unique y value. So this table of values remains a function. The same can be said if I enter option E. If I put 9 in for x and its corresponding y value of -5, nowhere else in these x values do I see a 9. So 9 only has one unique output, one unique y value. So adding 9 -5 to this table of values maintains the fact that this table is still a function. Now let's go to the next slide and show why the other points could not be added without disqualifying this as a function. If we look at the 4 points that are circled, for example, -11 and 12, we notice that there is another -11 here, and this has an output of 0. So adding -11 and 12 to the table would give me two different outputs, two different y values. Here -11 would have a y value of 0, and here -11 would have a y value of 12. So adding that point here would disqualify this table from being a function. The same can be said for option B. If I add -5, 4 here, I notice that this -5 already exists and it has an output of 3. Adding -5, 4 would give me a different y value, and that would also disqualify this table from being a function. If we look at option D, here we have an x value of 7, just like this. This x value 7 has an output of 11. Adding this one would give me a different output of 13. So adding 7, 13 here would give me two different y values for 7, and the table would be disqualified as being a function. And finally, let's look at option F. For option F, I see this has an x value of 2. However, there already is an x value of 2 with an output of -7. If I were to add this one, this would have an output of +7. So 2 +7 going into the blank spot here would also disqualify this table as being a function. And those are the reasons why these 4 points cannot be added into that blank space.